We've made it to pre-calculus. This is the last notes in chapter 0. So we are at 011. 010 didn't have anything new with it, just review of 8 and 9 and more problems with those exponents and rational exponents. We're going to look at radical operations here. We know radicals come from rational exponents, so how do we work with radicals? Big review of a lot of things we've started with here. So let's see, starting with add and subtract, doing all the operations with radicals. So add and subtract, remember we're looking for like terms on these. So like terms, remember you guys know that if we have 4x plus 2y, we can't add those together. If I put another 3x in here, we end up with 7x plus 2y. Like terms, same variable with the same exponent. When we do radicals, it's the same thing. They must be the same number inside the radical, that's the radicand, and the same type of radical, same index. So root 2 plus root 2, that's okay to do, that's 2 root 2. Root 2 plus cube root of 2, no, we can't add those. And it goes without saying root 2 plus root 5, no, not even the same number inside. So they have to be the same type of radical, the same index, and the same number inside the same radicand. So let's just take a look real quick here. You could even write these as x and y to try to get through it if you need to. But we have, let's see, 5 root 3 plus 1 root 3. Those are like terms. That's going to make 6 root 3. And the others are fourth roots, so they don't go with the other root 3's. But careful with this. That is a negative 6 fourth root of 3 plus 2 fourth root of 3. So that is negative 4. Keep that fourth root. Don't lose that root as you do these problems. 4 fourth roots of 3. All right, number 2, what we have to remember is even though these are different, doesn't mean we can't add them together. Always simplify first. So everything has to be simplified. Uh, 12, we got 4 times 3. 4 is 2 times 2, so 2 times 2 times 3. That is 2 root 3. Hopefully, a lot of these are pretty quick. Let's see, 75 is 25 times 3. That's 5 times 5 times 3. So that is 5. 3 left over, root 3. Yeah, that's good news. Same thing. 8 is 2 times 2 times 2. There's a pair of 2's. 2 root 2, not the same thing. So 2 of them we can put together. That's 7 root 3. 1 is not like the others. 2 root 2. So 7 root 3 minus 2 root 2. All right, multiplication. Multiplication. Well, it's just like variables. You can multiply 7x times 2y, and you just get one term with an xy with it. Same thing here. The only rule with these multiply, they have to be the same index of root. So the same index on the square roots multiply square roots. So square root 2 times square root 3, that's okay. We can do that. We can multiply the insides. Square root 2 times the cube root of 3, no, we can't. They have to be the same type of root. And the order was multiply the insides, multiply the outsides, right? So outsides multiply, insides multiply, and you need to simplify by the time it's done. There might be a couple places you can do that. Let's take a look at this first. Nothing simplifies here. You can't get pairs out of 6 or 10. So outsides, 6 times 5. We've got 30 for the outside. And our radical, we've got 6 times 10. So we've got 60, but always simplify your final answer, just like fractions. You always reduce fractions, you always simplify radicals. Let's see, 6, 10, that's 2 and 3 and 2 and 5. There's a pair of 2's in there. So we end up with 60, that's 2 times the 30. And we got a 3 and a 5 left. That makes a nice 15. So 60 root 15. All right. So what do we do with bigger numbers? We can definitely multiply these. We're not going to use calculators on it, but you can multiply these and do 24 times 15. It's not impossible to do. But there are some simpler ways. If you think about number 3, what we just did, we did 6 times 10 is 60. Then look what I broke it down to. It came from 6 times 10. That's what we started with over here. We could have just started breaking those down. Basically, a multiplication sign here just means it's all one big group. Let's just break them all down and look for pairs. So instead of doing square root of some big number, 24 times 15, I'm just going to think that's 24 times 15, all within the same thing. They're the same type of root. So it's like one big radical that's already partially broken down. So as I look at my 24, I know that's 2 times 2 times 2 times 3. And the 15 is 3 times 5. As a square root, I'm looking for pairs. Here's a pair of 2's. But I can also grab a 3 from each and say there's a pair of 3's. So my answer is going to have a 2 and a 3 on the outside. You can write down 6. We'll just simplify it. And on the inside, we're going to have a 2 left over and a 5. So 2 times 5, we're going to have a 10 left over in there. So instead of trying to waste time figuring out that number, 24 times 15, just go ahead and use that as your first split in your factor tree, 24 and 15, and go from there. Same thing with the x's. These are easier just to multiply. We just have to count them up. We have x to the fourth when we put those together. Square root of x to the fourth, remember we just divide by square root, so divide by 2. And that'd be an x squared, none left over. And we have y, let's see, y and y to the fourth, that's y to the fifth. So that's y squared, and there's one y left over. 5 divided by 2 is 2, remainder 1. So here we have 6x squared y squared. Say square root of 10y. All right, division. Division means with radicals we need to rationalize. Now here's the deal with rationalization. Um, Rationalization was important before there was a lot of calculators that could do fractions easily. Basically, we didn't want to divide by fractions. Um, so now it's easy enough to divide by fractions on a calculator, but rationalization has tools we want to be able to use, knowing this concept. Once we really get past this, a lot of things we are not going to rationalize. When we get to trigonometry, there's going to be certain values we just don't care about rationalizing. AP calculus doesn't care if you rationalize. So we need to know the skills that are behind this. That is the idea. Why are these things happening as we rationalize a denominator? And we have to be able to recognize when we have equivalent answers because of rationalization. All right, let's take a look here. So basically, we're working with the idea with square roots that we know the square root of something times square root of the same thing. That means the square root of a squared, which is just a. Rationalize means we need a rational number, something that's not going to be a never-ending decimal down there. We'd like a whole number in the denominator. So how do we make that happen? Think back to what you did a little bit in geometry, a little bit in algebra 2. The root 5 is the problem, and if we want to rationalize, we're going to multiply it, figure out what to multiply it by to make it a whole number. Well, the easiest way is just to copy it, root 5 times root 5. The real work would be that makes root 25, which is 5. We get 5 on the bottom. Now you can't just go around multiplying root 5s wherever you want. You got to balance it. So algebra, we can balance by multiplying by 1. That's written as root 5 over root 5. So remember, you multiply by something on top and bottom. We did that with complex fractions. We had to choose the right thing. Same thing on numerator and denominator. We choose the root 5 so that it just makes a 5 out of that. Root 13 times root 5, we can multiply the insides. That is 65. That breaks into 13 and 5. No pairs in there. So we're done. Root 65 over a whole number, 5. That's rationalized. So what does that mean when we have different roots? 2 over cube root of 9. Well, cube root of 9, here's the biggest issue that I usually see. It's easy to just think, oh, we just did a root, we repeated it right over here, root 5 and root 5, we just got 5. So can we just do cube root of 9 and get 9? That's not going to happen, because think about why that root 5 times root 5 turned into 5. The 25, the root 25 over here is really square root of 5 squared. We wrote it twice. And a square root and a squared, that's a 1/2 power and a 2 power. That makes a 1 power. So it's gone. It's just a 5. What this really makes is cube root of 9 times 9 is 81. We don't know the cube root of 81. We'd have to start simplifying it, and we'd still have a radical left. So that is not what we want to do. So how do we make this work? Well, we make it work by thinking of perfect cubes, if you want. And an easy way to do that is look at exponents. Now, if you think about perfect cubes right here, multiples of 9 that are perfect cubes. We know, let's see, 1, 8, 27. That's a winner. 27 is what we want. So 9 we know times 3. So we could do cube root of 3, top and bottom. And let's think that's cube root of 27. So we end up with just a 3 on the bottom. And on top, 2 cube roots, don't forget about that, of 3. There's our answer. Now, how can we make that a little bit simpler? When we're looking at cube root of 9, we want to think about the parts of this. So one way to say that is this is the cube root of 3 squared. 9 is 3 squared. So if we already have 2 3's, we need one more to make it 3 cubed. That's how we came up with this cube root of 27. You don't really have to think of the 27. We're just going to think about this as 9 is 3 squared times one more 3 makes 3 cubed. Cube root of that is just a full 3. We're trying to complete whatever index root that is. Cube root, I want to make 3 of each factor happen. So think about that on 4 over 5th root of x squared. So the important part's down here. The 4 doesn't matter right now. So let's think. I have 2 x's multiplied. I need to multiply by a 5th root, top and bottom. And in order to make it perfect on the bottom, if I have 2, I just need 3 more. And that makes x to the 5th. 5th root of x to the 5th. It's just going to be x. Those will cancel each other out. That's what we're making happen. So 5th root of x cubed. We just get an x on the bottom. That's what we wanted to happen. No more radical. And 4 times the 5th root of x cubed on top. So see if you can complete each factor into the right number. 5th root, we need 5 of a kind. Cube root, we need 3 of a kind. Square root, we just needed 2 of a kind. So we can just repeat ourselves. So see what you can do on number 8. A little bit more difficult. 2 over the 4th root of a bigger number, 24, x squared. Let's see, multiply by. I know it's going to be a 4th root. Get the easy stuff up there first. All right, now with 24, there's one of those. I could do 3 more, but that's going to be some big number I don't want to worry about. So we want the smallest one. Think about this x squared. We have 2 x's. We need 4 of a kind, so I need x squared. That's the easy part. And then my answer will have an x on the bottom, right? We'd have the 4th root of x to the 4th. That's what we're going to do with factors. Let's look at the factoring of 24. We've done this before. It's 2 times 2 times 2 times 3. Well, that means it is 2 cubed times 3. That's what we have out of the 24. Just do them separately. So we have 3 2's. We need 1 more. That would make 2 to the 4th. We have 1 3. We need 3 more. That's 3 cubed. If we do that, what all of this comes out to is the 4th root of 2 to the 4th times 3 to the 4th, and we have that x to the 4th. Well, the x to the 4th root gives us x. So each of these will give us the factors that were involved. 4th root of 2 to the 4th is 2. 4th root of 3 to the 4th is 3. So that's 2 times 3 times x, better known as 6x. That's how we break it down and think through it, so we don't have a lot of reducing to do later. So 2 times 3 times x. And then up on the top, we have the 2 outside. Don't forget about that. It's hanging out there in the numerator. Times the 4th root of, and let's just multiply this to make it one number. 2 times 3 cubed is 27 times 2 is 54. And x squared, we really multiply by 54x squared in the numerator and denominator. Now the 2 and the 2 here can reduce. So 2 over 6. We can get rid of those. So really what we're dealing with here is the 4th root of 54x squared. If you found the smallest multiple here, then you won't have any reducing to do in this 4th root of 54. There's no 4 of a kind in there. Over, the 3 is still there, over 3x. There we have it, rationalizing with higher radicals. All right, number 9. So instead of just a radical on the bottom, we have a binomial with a radical. Still can't have a radical on the bottom, so we need to be able to work with that. So let's think about some options we have here. We have a root 5. Simple square root, so let's just try root 5, top and bottom. I like to do things that don't work first. This is 2 root 5 over. Now you have to distribute this. There's our problem. 3 root 5 plus, well, this is good. Root 5 and root 5 is 5. But now we have the problem right here. That did not work. So let's get rid of those. Try it again. So just we think of radicals, same thing on the bottom. What about 3 plus root 5? So multiply by whatever's on the bottom. Well, again, here's the problem. This is a group of 3 plus root 5 times another group. You have to FOIL this out. And that is 9 plus 3 root 5 plus 3 root 5. That's 6 root 5. We still have a root. Plus, there's good news, there's a 5. Well, I still have a radical no matter what the numerator is. So that will not work either. All right, let's try something that works. In both those cases, we still had a root 5 somewhere in the problem. We're going to go back to a pattern we know. So the difference of squares are factoring. A squared minus b squared was a plus b, a minus b. Well, these are each something squared. Something squared gets rid of a radical. If we have a plus and we multiply by a minus, the same two values, we end up with 2 squared values subtracted. So we're going to build this difference of squares pattern. So remember, I think I said this in some of my classes. Can't remember, did it 6 times last week. A plus b times a minus b, same two values, opposite sign in the middle. They're not opposites, they are conjugates. Conjugates, just switch the sign in the middle. So we're going to multiply by whatever makes a difference of squares pattern. 3 minus root 5 on top and bottom. Remember, funny form of 1, something over itself. We get, I'm just going to write this right now as 2 times 3 minus root 5. Try to factor as much as possible, so why multiply it in if I can just factor it back out? And on the bottom, well, these conjugates multiplied to be a squared minus b squared, just the first one squared minus the second one squared. If we go through FOIL, 3 times 3, that's 3 squared, 9. The outside and the inside cancel each other out, plus and minus 3 root 5. And then the last one is root 5 and root 5, which is 5, and they're always opposites, will always be subtraction. It's going to be square the first minus square the second. That's backwards from the difference of squares pattern. So that's a quick way to always get that. You should be able to multiply conjugates pretty quickly. Like, try this. All right, so let's finish this out. We have 2 times 3 minus root 5. On the bottom, 9 minus 5 is 4. Always reduce your fraction. That's why I like having this 2 factored out. You can still see it if it's in there, but reduce that with the 4. Remember, to reduce, you have to factor a fraction. So factor it out and be able to reduce it. That makes a 2 on the bottom and just 3 minus root 5 on top. There is our rationalized form. Knowing about those conjugates is an important skill to use later on, even if we can just keep a radical down there. That's a skill we're going to use later in this year. All right, that's 0, 11. Go for that on the homework. Hopefully I have 8, 9. Where are we? 8, 9, 10, 11. Each of those be able to do with exponents and radicals, and this just finishes off with operations with radicals. All right, let me know questions again. And when we're back together, we'll be reviewing all of these things. All right, see you guys later.